Academic Physics, welcome back again to the Simpkins Physics Corner. Tonight, it is all about turning XT into VT graphs. What does that mean? Well, we've been talking about motions. So let's do a quick review of everything that we know so far. On a position time graph, which we call an XT graph, you can learn or you can describe things about an object's motion. So if we have a position versus time graph, wherever the y-intercept is, that's going to be the starting position or the starting point. All right, in other terms, we call that xi, right? The slope of the graph, we know that the slope of the graph, the rise over run, because the rise over run is delta x over t, that is our definition for how fast you're going. All right, so you can either get the speed from the slope, or actually, technically, you can get the velocity too. A steep slope means that you're going fast. A positive slope means you're going, gradual slope means you're going slow. A positive slope means you're moving forwards or in one of our positive directions, such as north or east or up. And negative slope means you're moving backwards or left or west or south, any of those negative directions. So there's just a quick recap of what we've covered so far. Now, before we jump into it too far, I want to get you guys familiar with this term, with these couple of terms here: average speed, average velocity, and instantaneous velocity. So average speed is like I'll give you an example of what average speed would look like. If you drive around small towns, especially, and here in Pennsylvania, the local police are not allowed to use radar guns, at least not as of 2018 when I made this slide. And the way that they enforce the speed limit instead is they have set up white lines on the road. And so your friendly neighborhood police officer will be sitting off on the side. They know the distance between these white lines, and they actually time you with a stopwatch when you drive from one point to the next. So when they do that, what they're doing is calculating your average speed. Why? Because they're doing a total distance over the entire time that it took to do that. So let's say you're sitting here and the speed limit is 35. And you just happen to have a little bit of a heavy foot today. Well, technically, if you are going 40 miles an hour when you cross the first white line, you could hit the brakes and slow down. And if your final speed was 30 by the time you reach the second white line, then your average speed, the average of 40 and 30, is 35. And so even though technically you were going faster than the speed limit at the first white line, the police officer has no way of knowing that because they're calculating your average speed. Now, if they were using a radar gun, however, then they would measure your speed at an instant. That's why we call it instantaneous speed. And that is the speed at which you are traveling at a particular one section or instant in time. All right, so average speed, if we consider that example and go back, average speed is distance over time over a long time period. Average velocity is displacement over time, but instantaneous velocity is your velocity at a particular instant. So a radar gun would measure your speed as soon as they pull the trigger to make that measurement. The timing method would measure your average speed. So let's consider this as we look at some position time graphs and translate them into velocity time graphs. So the first one says, how far did the object travel in 4 seconds? So this is a pretty easy one. I don't mean to patronize you with this. But if we start at a position of 0 meters and at a time of 4 seconds, we get to a position of 4 meters, well, then you traveled 4 meters in 4 seconds. Not rocket science. What is the average speed? Well, remember, speed is equal to distance over time. Oh, so I traveled 4 meters in 4 seconds. That must mean I was going a speed of 1 meter per second. Now, today we're going to look at how you get from the position time graph to a velocity time graph. You'll notice the velocity graph here. It's labeled as velocity on the y-axis, time on the x-axis. Our velocity, the average speed that we have, is 1 meter per second. Now, if you look at the graph of position versus time, you notice it has a positive slope, and we know that slope has a value of 1. So what would our velocity be then for this entire graph? Well, notice that this is a straight line, which means we have a constant speed, which means it doesn't change at all. And since the slope is positive 1, the velocity at the beginning is 1. The velocity 1 second later is still 1. The velocity 2 seconds later is still 1. The velocity at 3 seconds and 4 seconds. The entire time, the velocity is a steady or constant velocity of positive 1. So let's think carefully on this. At any point, if I were to put a straight line along this graph, that line would always have the same slope. It would always have the same steepness. Steepness of a position time graph is speed, or velocity in this case. And so that velocity, that slope of positive 1, tells us that the velocity is constant. So this graph right here shows us, if we were to read this graph aloud, we would say, oh, it's traveling with a constant velocity of 1 meter per second. Let's consider another example. How far did this object travel in the first 1 second? Well, in the first 1 second, it looks like we traveled 2 meters. And so if I say what was the speed, you would do distance over time, which would be 2 meters over 1 second. And of course, that would be 2 meters per second. That's how fast we were going for the first 1 second of this motion. How far did it travel from 1 to 5 seconds? Well, if we look, it looks like we went up 1, 2. So it looks like we traveled 2 meters. And what was its speed from 1 to 5 seconds? All right, well, from 1 to 5 seconds, we've seen this equation before of delta t equals t final minus t initial. All right, all that is saying is the change in time would be 5 minus 1, or 4. Not rocket science to say, 1, 2, 3, 4 seconds, right? So if we went 2 meters in 4 seconds, if we went 2 meters in 4 seconds, then our answer here would be 0.5 meters per second. What's the total distance traveled? Well, we started at 0 and we ended at 4, so we went 4 meters. And when it says what's the average speed, remember, even though I had two different instantaneous speeds, I was going fast and I slowed down and went a little slower, right? The average speed is just the total distance over the total time. So this would be 4 meters over 5 seconds. All right, and that's a funky number, but I guess it would be 0.8 meters per second. Now let's talk about the graph translation. I'm actually going to stack them to make this a little bit easier, okay? Let me steal these numbers, though, because in this graph, we calculated 2 meters per second here and 0.5 meters per second here. So I'm just going to kind of write that off to the side. First, we were going 2 meters per second, and then we were going 0.5 meters per second. You can check the work from the first part of the problem if you're wondering where that came from. All right, well, look at what happens. I line these graphs up like this because you notice that the 1 seconds are kind of aligned, right? The 1 second position on the position time graph and the velocity time graph are aligned. And so look what we're actually graphing down here. We're graphing velocity. And for this entire first 1 second, the velocity is a constant positive 2. What does that mean? That means the velocity has a constant value of positive 2 for the whole first 1 second. Let's continue on. You'll notice that for the next segment of the graph, there's an abrupt change. It's like an elbow, like that, on the position time graph. Now, you may have seen something like this in math class. Sometimes your teacher will draw a dotted line. Sometimes they'll just jump down. But what we know for sure is as soon as we're past the 1 second mark, we're now in this region where we're traveling at a rate of 0.5 meters per second. So that's why I jumped down on my velocity graph and I drew a point at 0.5. And then I'm going 0.5, and I'm still going 0.5, and I'm still going 0.5, and I'm still going 0.5. How did I know that? Look at the position graph. My slope was 0.5 steadily this entire time, so it would look like this. So this velocity time graph is showing we were going fast, positive 2, and then we dropped down to 0.5. And that's where we get the shape of this velocity graph from. All right, let's see all the details we can tease out of this position time graph. How far did the object travel from 0 to 2 seconds? Well, it looks like we traveled 2 meters. We went from a position of 2 to a position of 4. What's its speed? Well, if you went 2 meters in 2 seconds, not rocket science to say it's 1 meter per second. How far did the object travel from 2 to 4 seconds? Well, it looks like we started up here at 4 and we made it all the way down to 0, right? So it looks like we traveled 4 meters, but really we did that backwards. So I'm going to write -4, okay? And so then when it says what's the velocity from 2 to 4 seconds, remember velocity is displacement over time, and displacement has direction. So our direction and our magnitude and direction for the displacement is negative because we're going backwards, and 4, that's meters, and that happened in a duration of 2 seconds. So our velocity would be -2 meters per second. What's the total distance that we traveled from 0 to 4 seconds? Now, this is a little bit tricky, right? This is a little bit tricky. Because what we actually did is we went from 2 to 4. So how far did I go? I just traveled 2 meters. And then I went from 4 down to 0. How far did I go? 4 meters. So even though we went forwards and then backwards, remember the definition of distance is that every step counts. So that 4 plus 2 gets us 6 meters. Then it says what is the object's average speed for 4 seconds? Well, speed is distance, 6 meters, over time, 4 seconds. So that would get us 1.5 meters per second. What's the object's displacement? Now, here's the difference, right? Displacement is how far you went from this place to that place. I know you hate it, but it's a great way to remember. And so our final position, if we do delta x, our initial position was 2, and our final position was 0. So 0 minus 2. Our displacement from start to finish was -2. And if that's the case, velocity being displacement over time, that would mean it would be -2/4, or -0.5 meters per second. That's the average velocity. At what time does the object turn around? Of course, that would be right here, because it was going forward and then it starts going backwards. So that's at the time of 2 seconds. All right. And it says, at what position does the object start? Obviously, that's 2 meters. Let's look at the graph conversion from position to velocity. Let's pull those numbers real quick. The speed was 1 meter per second. You can see it's just one block over one block. And then it was -2 meters per second. So let's look at the translation here. First, we were going at a speed of +1. So I'm going to track with this. +1, +1, +1. The reason our graphs for velocity are so boring right now is because our position time graphs are straight lines. And straight line means constant speed, and constant velocity on a velocity time graph shows up as a horizontal line. Why? Because the velocity is 1. And then what is it? It's 1. And then what is it? It's still 1. Okay, so that's why they look different than the position time graphs. Then this is going to jump down all the way down here, and it's going to ride the rest of the graph at -2. Why? Because we were going backwards 2 meters every second from 2 to 4 seconds. So here's what I want you guys to do to check your understanding of this lesson. This is what I would like you guys to turn in. All right, I would like you can take a screenshot of this, you can snip this, or you can download it from Canvas. All right, let me move my face a little bit out. Yeah, face is right there, it's fine. I want you to sketch the position time graph for this scenario and the velocity time graph for this scenario. So here's the scenario. A man walks from x equals 2 meters to x equals 6 meters in 6 seconds. The one thing I want to change here for you guys is just make this number say 6 and make this number say 3, and it should work out just fine for you. All right, so if that's 3, then this is like 2, 1, and it's like 4 and 5. All right. Then he turns around and he walks from x equals 6 meters to x equals 0 meters in 2 seconds. So he's going to go forwards, and then he's going to turn around and come backwards. What I need you guys to turn in, if you go to the Canvas assignment, is I want you to look at this story, draw the position time graph, and then using what you just learned in today's lesson, also draw the velocity time graph. The only thing I want you to turn in is I just want you to snip this with your final answer. So snip this right here with your final answer, showing me what your graphs would look like for this story. Okay, so that's it. I hope you guys enjoyed this lesson, and if you stay tuned for some more physics coming at you next week in the Simpkins Physics Corner, we're going to be wrapping up our unit here on motion, and we're going to be getting into acceleration. So have a wonderful wherever you are, whenever you are, in the Simpkins Physics Corner.